what we have been saying so far, is always get to have a perspective. So we have a differential manifold. Yesterday we saw when is a topological manifold differentiable. And at the back of our mind, we know the dimension of the manifold is n, because this differential manifold, there are these open sets and the homeomorphism constituting the charts, and the collection of charts is called the atlas, and it is mapped to Rn because there are homeomorphism from the manifold to the Rn. So we know that the dimension of M is also the dimension of Rn, and hence we are characterizing the manifold to have the dimension n. And then we, if we look at any particular point P belonging to the chart U endowed with a homeomorphism from the open set to an open set V here. At the point P, we figured out that you could have a tangent space. So here is a tangent space. The vectors V belong to the tangent space at point P. Similarly, we defined the one forms. Let's denote the one forms as how do I denote? I mean, you can generally call D of F, one forms D of F, which are essentially objects that operate on TPM to produce real number. In particular, D of F acting on a vector that is denoted as D of F acting on a vector V is same as the V operator acting on the function producing a real number. And then we talked about the fact that you could have different kind of bases. In particular, the coordinate bases in plural, because you have, for the vectors, you have the basis coordinate basis del by del x I going from 1 to n. This is the basis for vectors. Remember the vectors, these are all at a given point, because now we are going to talk about vector fields. And similarly, the basis D of xi, again I going from 1 to n for the one forms. And this is an example of a orthonormal basis, meaning that these basis vectors D of xi acting on the vectors del by del xj is same as, because this acts on the function, V acting on the function, here the function is xi, which is del xi by del xj, and this is Kronecker delta ji, and hence we know that it's an orthonormal basis. All these we were talking about the structures at a given point. But then we can say that these tangent space, so the tangent space TPM and one forms, the collection of all one forms belong to the dual space T star M they, although defined at a given point, but this point is arbitrary. You can do it at different points. And therefore, we can have a full vector field. In physics, the mathematics field is different from physics field. In physics, when we say something is a field, what we mean is that's a function of points. Okay. Mathematicians' fields have different properties. Fields are a set of elements in which both addition and multiplication is defined. But when I say vector field, the vector field is vectors defined at every point on the manifold. Similarly, when I say one form fields, they are defined everywhere in the manifold. Okay. So now we are talking about the full manifold, vector fields, and dual vector, or same as one form fields and one form fields. And it's a trivial generalization, just like in terms of the basis vectors, a vector at point P can be written in terms of the components Vi at point P, del by del xi. Okay. And similarly, one form, any one form d of f can also be written as del f by del xi d of xi. Okay. This is again at a point P, and so this is a covariant vector. Del f by del xi is a covariant vector. Let us call this. By the way, probably I should have been using upper index for the coordinates. These are all upper index. Just for the sake of notation, it doesn't matter. These are all upper indices. Just to stick to the notations for consistency's sake. Now when we say vector fields, what we mean is now V is defined over all points over the manifold. So in other words, it can be written as V of x, where x's are the coordinates. By virtue of the homeomorphism, we know these are the coordinates of the points. So I will not write x1, x2, xm, it's implied. All the coordinates are there. Vi of x, del by del xi. Similarly, the one forms, any one form, d of f can be written as, now these are fields. They are defined all over the manifold. I can write it as del f by del xj of x. And as we said, and this is same, I mean, if I define del f by del xj as omega j, then as we mentioned that the components, these are the components of the vector, and these components, when you make a coordinate transformation, that means you have different charts, they will transform as a contravariant vector, while these will transform as a covariant vector when you make coordinate transformation, although the vector, the abstract vector or the abstract one form, they don't change. Okay, all right. So we have the vector fields, we have the one form fields. Now we can talk about arbitrary tensors, because remember, you can always take tensor products of one form basis, tensor products of vectors, also tensor products of combination of one form basis elements and vector basis, and hence we can now talk about a general tensor field. Okay. So a general tensor field T can be written as this is also a field, so it will depend upon the all points on the manifold, or equivalently in the Rn, it will depend upon the coordinates, and the coordinates are there all over Rn. And the way I have written, you can easily see that this is del by del x I1 tensor product, del by del x I2 tensor product, so on. And what is the last? Yeah, del by del x IR. And similarly, there are these lower indices. That means there are tensor product with one form basis vectors, which are, I have chosen coordinate basis, but you can do it with any abstract orthonormal basis vectors. So, in the standard tensor calculus terminology, this is a mixed tensor of rank, contravariant rank R and covariant rank S. Sometimes it's called SR or RS tensor. So, as you can see, you're having a correspondence from differential geometry to the standard tensor calculus. And as I said, that towards the end today, from that onwards, I will stick to tensor calculus. Okay, and but of course I will define the relevant machineries to do if you want to use differential geometric technique, the relevant mathematical tools I will introduce. After that, I will use the standard tensor calculus. The reason is that we have to go quickly to several important results in GR, and that's the reason if I stick to differential geometry, those things cannot be covered, because say only 10 lecture course has that constraint. Right. So now you see that a arbitrary rank tensor, how to express it in the differential geometric form. And so when you make a coordinate transformation, these components change. By the way, Einstein summation convention, whenever indices are repeating, they are being summed from 1 to n. I1 is repeating, so I1 is being summed from 1 to n. J1 is repeating, they are summed from 1 to n, and so on. So components of the tensor, they will change if you make a coordinate transformation, but the abstract tensor T, that doesn't change, just like V or the one forms. Okay, that was one of the greatest achievements in differential geometry, to say what are the vectors, what are one forms, or what are tensors. These are abstract objects. Vectors are like operators, one forms are like operators acting on vectors, and so on. All right. Now, yesterday I talked about higher form. Higher forms are achieved by using antisymmetrization. So if you talk about, okay, so zeroth form, zero form, any normal continuous function, the set of all functions, now I'll call X because these are fields now, set of all function is a member of the zero form space. Remember zeros form. Now earlier I was designating in terms of point P, now we are talking about fields. So entire manifold. Okay. So is a member of this space. Okay. So the class of all continuous and smooth functions, they form the set of zero forms which reside in this. And because we are now talking about fields, so that's why earlier I was yesterday denoting as omega 0 p. Now we are talking about manifolds. One form, we have already encountered one form fields. So class of all objects which can be written as d of xi times some arbitrary scalar field phi of x. In coordinate basis, of course, in general. So this belongs to omega 1 m. From here and here you can't distinguish what is so great about omega 0 m and omega 1 m. After all, they are all the same scalar field and one form fields. But the moment you come to two form, you realize the difference. Two forms are all of the type. So Fij, so it's a tensor product dxi dxj minus dxj tensor product dxi. So it is now antisymmetrized tensor product, and therefore Fij becomes antisymmetric. And this belongs to omega 2 m. So in other words, any p form, so you can generalize it. So the whole thing can be generalized. And this object, by the way, this antisymmetrized thing, this is you can have a short form notation. This whole thing is denoted as wedge product. We will talk about the properties of the wedge product soon. Is antisymmetrized, so dxi wedge product dxj is same as minus dxj wedge product dxi. And a arbitrary p form can be expressed, the class of all objects of the form 1 over p factorial alpha I1 I2 up to IP dx I1 wedge product dx I2 dx IP. So class of all, now these are all, so it's an antisymmetric tensor, covariant tensor, and class of all such function forms, is a member of omega pm. Okay. All right, so now I'll erase this part of the blackboard and we'll talk about properties of forms, then what are the properties of this wedge product and so on.
Sorry,
Yeah.
form 1 factorial will be there then.
Oh, sorry?
General P form, there is P factorial.
Yeah, so the p fact, you can ask why p factorial is here, because it's being summed over and you will be overcounting. So, and it's already antisymmetric, this is antisymmetric, this is antisymmetric. The overcounting, to not do the overcounting, we do the p factorial. That's the important point. Let me show by using a simple example. Suppose I take a 2 form. So if I write the 2 form, for example, in your electrodynamics tutorial problem, if I write the 2 form as f mu nu dx mu dx nu, the wedge product, if I do this, Remember, mu is being summed over. Okay? So therefore, if you sum it over, then you will find that you will be overcounting, because when mu is 1, nu is 2, then you have 1, 2, but then we will have, when mu is 2, this is 1, we will have 2 and 1, but this is identical because of the antisymmetric property, and that's the reason, to avoid overcounting, you have 1 over 2, which is same as 1 over 2 factorial. And that's the reason why you have this p factorial in order to avoid overcounting.
Okay, so in that 2 form it will be Fij by 2 factorial?
Exactly, exactly. Not to, because I had introduced this notation, but when you use this notation, there will be a 2 factorial. Yeah. Right. Now let us give, you can of course derive it by doing this antisymmetric thing, but there are these important properties. When you do manipulation, you can use these properties in a shorthand so that you don't have to go to the first principle of using so many wedge products of one form basis vectors. Right. So properties of wedge product, properties of wedge product. So first property, if alpha, I mean what I am going to write down, it is obvious. So if alpha is a p form, then a 0 form f. By the way, now I am suppressing the script argument x. We know that these are now fields. We are now talking about forms over the entire manifold. They are fields, but in the back of the mind we know that this depends upon x. So if and f of x is a 0 form, then f of x wedge alpha of x is same as alpha of x wedge f of x, and it is same as f of x, just f of x multiplied by alpha of x. But there is no point in distinguishing because alpha is a 0 form. All right. And you can using, because why f of x doesn't have a dx with it, alpha will have dx, so it doesn't matter how you write it, and hence f of x alpha x, where f of x is just a function, is simply they commute, and hence you can just write it as f of x alpha x, and this is a p form. So if you multiply any function to a p form, it remains a p form. Second property, if alpha is a p form and beta is a q form, then alpha wedge beta is minus 1 to the power p into q beta wedge alpha. All right. You can show it using dx dy, but you can prove that this is indeed true. Okay, you can show by just using all these wedge products, by just taking it the other way and all that. You can show it, but you can prove this is indeed true.
Can I ask a silly question?
Yeah.
Property,
What?
the first property,
Yeah.
the wedge product is defined in the antisymmetric way.
So wedge product is always antisymmetric, but there is only one dx because alpha fx doesn't have a dx in it. These have dx.
It doesn't have two terms. It will have only one term.
No. Alpha will have, in terms of dx, it's a p form. So there will be dx I1, wedge dx up to dx ip. But f doesn't have any dx.
Isn't it fx the tensor product of alpha minus alpha?
Yeah, so this wedge happens to be same as tensor product. Because this is a zero form. Yeah. By the way, you can see from here, it follows, this also follows. Why? Because if alpha is a zero form, p is 0. 0 into q is 0. Minus 1 to the power 0 is 1. So it doesn't matter how you write it. Then all those associative properties are trivial. That is, alpha, wedge, beta, wedge, gamma, the same as alpha, wedge, beta, wedge, gamma. That means if you take alpha, take another form which is beta, wedge, gamma, do the wedge, is same as taking taking a differential form alpha, wedge, beta, and then taking the wedge product with gamma. These are all obvious in the sense you can derive it from the wedge product definition, completely anticipated tensor products. Am I missing some other properties? So let me see.
So can you alpha wedge beta in alpha is a p form and the other is a q form? Is it minus 1 raised to p times q?
PQ. That is, P is a number, Q is a number, its product P into P. Let's see which are the other properties which are very important. There's another property. Yeah. If you take a zero form, multiply with a p form, if alpha is a p form, then we have already stated f into alpha is also a p form. Then this wedge, another differential form, beta, is same as alpha, wedge, f to beta. So in general, it can be written as f times alpha, wedge, beta. These are obvious properties, but it is good to summarize so that when we are doing manipulation, one shouldn't be going back to the first principles and re-deriving everything. Okay. Now there's a surprising result. What is the surprising? By the way, this result is consistent with the fact dxi wedge dxj is minus dxj wedge dxi. That's obvious because if you take two 1 forms, 1 into 1 is 1, minus 1 to the power 1 is minus, so obviously it's antisymmetric. But the surprising result is this. So one of the corollaries of this. Let's talk about alpha wedge itself. What did you intuitively think? Wedge product is antisymmetric, so alpha must be minus alpha wedge alpha, should be 0. The answer is no. So that's a counter, use that. Suppose alpha is a p form. So this, according to this property, it will be minus 1 to the power p into p, p square, alpha wedge alpha. Okay. So if p is even, it is alpha wedge alpha. It's not 0. So this implies if p is odd, then alpha wedge alpha. If p is odd, meaning what? Any odd number can be written as 2n plus 1. 2n plus 1 into 2n plus 1 is 4n square plus 4n plus 1. It is odd. So therefore, you'll get minus alpha. So this makes it minus alpha wedge minus alpha, which makes it 0. But if P is even, it's non-zero. Okay? All right?
So if alpha and beta are both alpha, if beta is alpha itself. So I'm talking about the alpha wedge beta when it is two form.
Two forms.
Yeah. So when alpha and beta.
So for even thing, so because there are two form, even, 2 into 2, 4 minus 1 to the power 4 is 1. So therefore, if alpha is a two form, alpha wedge alpha is alpha wedge alpha. So they are not 0. It's not 0.
But is according to this definition, it won't be like alpha wedge alpha minus alpha wedge alpha, which is equal.
No. That's very important. dxi wedge dxj by definition is dxi tensor product dxj minus dxj tensor product dxi. This is only about product of two unforms, not about wedge products of general p forms.
So if alpha is a B form and beta is a Q form, what will be the wedge product? What will be the form? It will be.
No. This is the general result that alpha is a p form, beta is a q form. Then the product, if you want to write it as beta wedge alpha, this is the general result. Now, suppose always it's better to take examples. So you give me the value of p and q and let's see what we talk about. So give an example of p and q, actual concrete number. So let's say p is 2 and q is 3. How will you write alpha? Alpha can be written as, in terms of components, 2 factorial alpha j1 j2 d j1 wedge d j2. Okay. How can you write beta? 1 over 3 factorial beta I1 I2 I3 dx I1 wedge dx I2 wedge dx I3. Okay. Now if you take alpha wedge beta, there will be dxj of I wedge dxj2 wedge dx I1 wedge dx I2. So it will be a 5 form now. So Devrat, what's your question?
Yeah, that's what I was wondering. What should be the form of that wedge?
Yeah. So ultimately, in terms of basis one forms, you can express any p form. Now that you have asked this question, we'll talk about a very interesting property. Okay. Here we have talked about p form belonging to omega pm. First question, can p be any number? Can I take p to be any number? Can I go to infinity?
Function spaces are only up to the dimension of the manifold.
Exactly. Good. So you can go only up to omega nm. Why? So let's show it. Suppose you have an n form. So let omega be n form. Okay? Means what? I can write omega as 1 over n factorial and its components in multiplied by so on up to dx in. Okay, this is n form. Agreed? This is completely antisymmetric, this is also antisymmetrized, and if you finally do all the calculation, okay, show it for 3 forms, you will realize, you will do all the calculation, finally it will turn out to be W1, 2, 3, N, dx1 wedge, dx2 wedge, dx3 up to dxn. Because you are summing up, I1, I2 are all being summed over. But this is completely antisymmetric. Because it's completely antisymmetric, there's just one component which is non-zero. And you can write it as this. So this is the n form. Okay? Now I want to get a higher form, n plus 1 form. What will I do? Supposing I want n plus 1 form. What I will do is, a simple thing to do is, take wedge product with another dxi. Okay? But wedge product with another dxi, if I take any other dxi and sum it over, the I is running from 1 to n. Whatever that is, it will be either 1 or 2 or 3, etc. But it's completely antisymmetric wedge product. So it will be 0. I hope that means what? Supposing I wedge this dx1, dx2, dxn, and I wedge it with dx3. But this term 0 because there's a dx3 here, there's another dx3 here. The antisymmetry thing itself is telling me 0. Why? Because of this general result that if p is odd, this is 0. And dx is a one form, another one form, same one form, if I multiply, there's anti-commutation property, so it's 0. Okay? Therefore, in a n-dimensional manifold, the maximum you can go for a p form is when p is n. Beyond that, you can't. In fact, an n form is equivalent to, when we come to Hodge star duality, we'll see that there is a correspondence. Anyway, I shouldn't be jumping the gun. We'll talk about Hodge star duality soon enough. Okay. All right. So, we have covered the properties of the n form. Now we will go to the exterior derivative. We talked about exterior derivative briefly yesterday, but more details.
I don't understand why the only one component of the omega survives.
So go see, omega I1, I2, In is completely antisymmetric. Completely antisymmetric. That means you take any component, omega 3, 2, if I repeat any index, it is 0. So the only way you have a component which is non-zero is when I1, I2, In is a permutation of 1, 2, 3n. Only a permutation. But because of antisymmetry, any permutation is either plus or minus of omega 1, 2, 3n. Okay. So therefore, algebraically, there is only one component which is non-zero. Okay?
And P because the basis vectors of the space is n-dimensional. And basis vectors are n-dimensional. So
No. Basis vector is a one form. Basis vector is a one form, and there are exactly n independent basis vectors. Yeah, it is what you are saying is a related, but there is something more. That yes, there are only n independent d tilde x's. To create a n plus 1 form, I have this, I have to wedge it with another dx, but that dx will be either I1 or either 1 or 2 or In. But the moment two of the dx's repeat, the wedge product is 0. So, n-dimensional only n basis way, and the fact wedge product of two one forms is antisymmetric. Both facts make this.
Again, could be very silly. Whenever we write a form in that notation, like Fij followed by the wedge product, so this Fij, this is always anti-symmetric by definition.
No. Wait. It depends whether you are putting the alpha, the p factor or not. So if you don't put 1 over p factor, if you just keep it like this, that's the question, if you just keep it, but this is antisymmetric, so you will do all that and you will find even if there was a symmetric part of Fij, that term will be 0. So, but it's an important question. Supposing, you see, any tensor, second rank tensor, can be written as sum of even and odd. I hope those who have done tensor calculus, they know how to do that. So take any, so B mu nu is a second rank tensor, but B mu nu can always be written as B mu nu plus B nu mu, okay? Or there's another way of writing it. I can write it as B mu nu equal to B mu nu minus B nu mu plus B nu mu. Okay. And this can be written as,
One symmetric part and the other one is
yeah.
antisymmetric.
So therefore, I can decompose is a B mu nu plus one symmetrized B mu nu. This is symmetrized plus half B mu nu minus B nu mu. Okay, because this cancels. And this is symmetric, this is antisymmetric. So any tensor can be written as a combination of symmetric and antisymmetric. Okay. The wedge product, when you take a symmetric part, dx mu dx nu, when you take, it will be 0. So even if you had a symmetric part, that will not appear here, because dxi wedge dxj is antisymmetric. Okay.
So how do you express G mu, the metric?
Metric tensor is not a form. We'll come to that. So metric tensor is symmetric. But if you, even if you had added an antisymmetric term, because it is not dx wedge dy, is actually a tensor product, that part would go 0. So we'll come to metric. I have not yet introduced metric tensor. Okay? All right. Now I will have to erase this part. I will talk about exterior derivatives. By the way, now the power has come, no? I can continue. Yeah.
If we, let's say, even form and an odd form, and the obtained form is symmetric in alpha and beta.
Symmetric in alpha and beta meaning?
Alpha wedge beta will be beta wedge alpha.
This is the property. Only way alpha wedge beta can be beta wedge alpha is P into Q. If P into Q is even.
So if 1 is even, means if P is 1 or Q is 2,
Huh.
like 1
If 1 and 2, 1 and multiplied by 2 is 2, again even.
if that obtained form, will it be symmetric or antisymmetric?
Symmetric and symmetric meaning what? I mean, you take a 1 form and a 2 form. So let's, so a single form can be written as df. Then you take a wedge product with a 2 form. So a 2 form, as we were talking about, Fij wedge dxi wedge dxj factorial 2. Now what do you want to say?
Now we have obtained a 3 form, right?
It's a 3 form.
Will it be symmetric?
No, symmetric in what? I mean, this way it is symmetric. It can be, it is same as 2 factorial, the 2 form f, wedge d of f. Why? Because there's a dxk here. There's a dxk, okay. Now commute this so that now dxi is there, dxk is there. It will pick up a minus sign. Again commute dxj with dxk. Another minus sign will, minus minus becomes plus. That's how that property has been derived actually. Okay, now exterior derivative. So exterior derivative is a mapping. What it does is it takes the omega k on the manifold M to omega k plus. And we have encountered exterior derivative when we are talking zero, its action on the zero form. D of f, I mean, right, we already started with that, is simply del by del xi in dx. But now we want to know how to take exterior derivative on higher forms. Okay. So let alpha be a p form. So if alpha is a p form, alpha can be written as we were discussing earlier. Again, Einstein's summation convention, anytime two indices repeat, they are being summed over from 1 to n. Okay, so this is a most general p form, all right, and we want to take the exterior derivative d of alpha. One over p factorial. Now this is a function of x. Remember, we are talking about fields now. Everything is dependent on the n coordinates. So d of alpha, the way I took d of f will be a derivative of this. So therefore, there will be a derivative of alpha j1, j2, jp with respect to some del x jp plus 1, let's say. But then I have to put d tilde x jp plus 1 and wedge, rest of the wedge.
Those should be J1, J2.
Huh? What? Correct. Good, thanks. J1 wedge. Okay. Now clearly this is a p plus 1 form. So this belongs to omega p plus 1 of m. So this belongs to omega p of m, but there is an additional one, 1, 2 up to p plus 1. So this is a p plus 1 form. Again, because of this part being antisymmetric, this was already antisymmetric, but there is now del by del x shape. You have to antisymmetrize it. When you antisymmetrize it, you will find a combination. You will get 1 over p plus 1 factorial and a antisymmetrized derivative tensor of this. You can do it very easily. I am not going to spend time as to how to write this as a antisymmetrized p plus 1 tensor, but it can be done. A little bit of algebra is required. So therefore, now we know how to take exterior derivative of alpha. But then from all these, you can get a property all right? You can find out, so I'll now list some of the properties of exterior derivative. So first property, exterior derivative of alpha wedge beta is, so it's linear, no, not wedge, first you take addition. If you have alpha a general P form, beta also is a general P form, then you can add two P forms and you'll get a third P form. Then you have this. The second property is, if alpha is a P form, then D of alpha wedge, beta can be any form, is same as minus 1 to the power. Okay, first let's write the first term. D of alpha wedge beta plus minus 1 to the power P alpha wedge d of beta. Okay. All this, by the way, all this can be derived using this thing. But it's better to have the results so that we don't have to go to the first principles to derive all that. So note, the Leibniz rule, there's a modification of the Leibniz rule. See, what was our Leibniz rule, the derivative rule? Normally, if you have two functions, the Leibniz, the differential satisfies the Leibniz rule, f into g plus df into g, right? This is the Leibniz rule. But the Leibniz rule gets modified as far as exterior derivative is concerned. This is very important. There is a difference when we are talking about exterior derivative, minus 1 to the power p. Only if the first p form alpha is where p is even, only then you have the strict Leibniz rule. Otherwise, there is this minus 1 to the power p factor coming in. Again, this is counterintuitive.
Is that not because of property of the wedge product?
Yeah, it's because of properties of the wedge product. So, properties of the wedge product. On the other hand, it was tensor product, Leibniz rule would have been valid. But because it is antisymmetrized, the wedge product is antisymmetrized, you have this Leibniz rule gets modified.
There beta is just one form.
No, any form, any Q form. All right, so what is the other interesting properties? Yeah, the most important property. How come I have not written it down? Yeah, but that's the most important property. Yeah, so you take the exterior derivative of d of alpha, where alpha is any form. This is identically 0. Sometimes it is loosely referred to as, I will not go into that, it is referred to the fact that boundary of a boundary is 0. As you know, if you have a circle on the two-dimensional plane, this region has a boundary. The full circular area has the boundary, namely the S1. But you can ask, what is the boundary of S1 itself? S1 doesn't have a boundary. On the other hand, if you had just one segment, a line, it has boundary. These 2 points are the boundary. But the circle doesn't have a boundary. So this rule is really, I will not go to the integrals using but that by itself is a very interesting part of differential geometry. How the differential forms can be integrated is related to that. I will not go into that. Okay. And this follows again from this result. If you take d of that will be what? If I try to take d of this, there will be another derivative, del of del xg plus j plus 2, and there will be djx plus 2. But partial derivatives commute. Wedge products don't commute, but partial derivatives commute. So therefore it will be 0. I hope you understand the logic. It's so important that let's do it for a specific case so that you understand what is the reason why this is happening. Okay, let's do it and show that a very specific example we'll take. Suppose I take a one form. Okay, one form which is d of f. Okay, d of f can be written as del by del x I of f d wedge xi. Okay, all right. Now let's take d of f. D of f will be what? By definition, it will be del 2f del xj del xi d of xj wedge d of xi. Okay? Because remember, by definition, how do you take d acting on p form? It is through this. Okay, but this object is 0. Why? Because del 2f by del xj del xi partial derivatives commute. So del 2f by del xj del xi same as del 2f by del xi del xj. But dxj wedge dxi is minus dxi dxj. That is antisymmetric. So this is symmetric, this is antisymmetric, and therefore the product necessarily is 0. That's how you get this result. And this is very important when you do Stokes' theorem. You know, Gauss's theorem, Stokes' theorem, they get very beautifully, in a short way, it comes from the integral of differential forms. That I'll not have time to cover.
Can you explain this again?
Which one?
This, how did it come to 0?
Yeah. So, okay, so let me do it in detail. So that you see what is happening. Remember, j and I are being summed over. So what we have shown is d2 or d acting on d of f. We have shown is del 2 f del xj del xi dxj wedge dxi, where I and j are being summed over from 1 to n. Okay? But this can be written because they are being summed over. It doesn't matter what, I can call j as I and I as j. I can call it. No? So this is same as del 2 f by del x I. Wherever there is j, I'll call it I because anyway they are summed over. They are dummy variables. Okay, so this is same as this. But dxi wedge dxj is minus dxj of dxi. Why del 2f del xi del xj is same as del 2f del xj. So this is minus of this. Anything that is negative of itself is 0. Okay?
But it is counterintuitive. When we say zero derivative, we apply, suppose on one form we should get two forms.
What?
I'm saying
Huh.
But by definition we define this as it transforms from k to k plus 1.
Huh.
So now if we assume there is a one form and we apply extended, we will get
No,
two forms.
this is for general form. You take alpha to be a general form. D of alpha, if it is a p form, D of alpha will be p plus 1 form. But
Now that p plus 3 you again apply, then we should get p plus 2 form.
no, but if that form, if p plus 1 form, I'll soon come to certain definition. If the p form, p plus 1 form is D of a p form, then D acting on that will be necessarily 0. That's what we are seeing happening. It can be proved. I have given the example by taking alpha to be a 0 form, so that D of f is a 1 form. So what have I explicitly shown? That if I take a 1 form which is D of a 0 form, then that 1 form's, if you again take D of that, is 0. But it doesn't mean that for a arbitrary 1 form, D of that arbitrary 1 form is 0. That doesn't mean. Only for a 1 form which is of the type D of f, when you apply D, it will be 0. But there could be other 1 forms which is not expressible as D of f. For that exterior derivative, it will not be 0.
So that means there are other ways to get k plus 1 from.
No. We have to be logical. What I have explicitly shown, all the 1 forms which are obtained by taking exterior derivative of a 0 form, when you apply D on it, it is 0. But not all 1 forms are of the form D of f.
Are you asking why this definition doesn't work here? I mean, omega k goes to omega k plus 1.
Yeah, that is what I asked.
But it is 0, not 0 form. It is 0.
Yeah, I understood that.
So, yeah.
So is it somehow related to the vector identities that there is no curl of a gradient?
Yeah, it's all related. Absolutely. Absolutely.
So why not all one forms are the form of a D of alpha?
What?
So why not all one form are of the that form D form?
No, not you can have 1 forms which are not of the form D of f.
Can you give an example?
So yeah, example like.
No, your let's consider one example. So consider, because after all we have basis vector. Consider a one form which is of the type, okay. So consider a 1 form. Let alpha be a 1 form. By definition, if it is a 1 form, then it is alpha d of xi by 1 over factorial, but 1 factorial is 1. Any 1 form can be written as this. Agreed? So this is a 1 form. Agreed? But d of alpha will be del alpha I by del xj dxj wedge d of xi. Agreed? But this is not 0. Del alpha I by del xj, you can write it in the antisymmetric form. This is same as 1 over 2 factorial del alpha I by del xj minus del alpha j by del xi. But this is not 0. Unless the curl, I mean in 3-dimensional notation, only if curl of the vector alpha is 0, only then it will be 0, otherwise not. Now this is very important, good that you asked this question. These are very basic stuff, and I mean the power of mathematics is mathematicians ensure there are no loopholes. That's the power of a logical system. Okay? Yeah, so I will end our discussion of exterior derivative by some interesting observation, but I will not go into the details. This is Poincaré's lemma or Poincare. What we were discussing was related to Poincaré's lemma and inverse of Poincaré's lemma. But before that, some definition. Yeah, so I have to remember what is the closed form, what is the exact form, because I have a very bad photographic memory. So sometimes I interchange. So yeah, so exact form is that and closed form is that. Okay. So exact form. A P form alpha is said to be an exact form if and only if and only if there exists a form beta such that alpha is the exterior derivative acting on beta. We were actually discussing all that, but with respect to zero form. So only if you have a form which can be obtained from another form by applying an exterior derivative, only then that form is called exact form. But there is another kind of form which is called closed form. What is a closed form? If you have an exact form, d of an exact form is identically 0. That was happening, that because we are considering one form which is d of f, that's the reason why d of f was 0.
So there are certain geometrical objects from whom we can get the exact form. So there are certain geometrical objects for whom we can get the exact form, like circle we can get the exact form.
No, circle is not a form. Circle is a manifold. Circle is not forms. We have already defined what forms are.
Sir, Banach identity will be applicable for circle.
What identity?
So Banach identity, let's d square of Bianchi.
No. That is a separate. I will not cover that in my lecture. There is another operation called delta operation, which is used using Hodge-star duality and the exterior derivative. You are probably referring to that. I will not come to that, which is related to the boundary of a manifold. I will not discuss it because it will take us beyond. Yeah.
So as he pointed out that exterior derivative of an exact form always gives 0. But who will guarantee me that beta is an arbitrary form or one form of a 0 form?
Yeah, exactly. So I said there exists at least one. Okay, but you can see that suppose I take, so this is a beta is a form. I take another form beta prime, which is beta plus d of gamma. Then d of beta prime is d of beta, but d of gamma is 0. So d of beta prime is d beta, and therefore it is same as alpha. So beta is not unique. There exists at least one beta, then of course there is exact form, but beta is not unique. If there is one beta, I can always add to that beta d gamma, you will get the same result. What does this remind you? Gauge symmetry. In electrodynamics, I think when you did the problems, when Bhashwati did the problems yesterday, A mu, so since the power has not come, we can, it has come? Okay. So it is associated as an application, it is the gauge symmetry, because your A, the vector potential, is a one form. And you can add to it another D of a scalar field, nothing will happen. If you apply D on A, you'll get, okay, so this is related to gauge symmetry. Yeah, so closed form, P form is said to be closed if and only if P form gamma, let's say, or anything, gamma, is said to be closed if and only if D of gamma is 0. So, any P form gamma for which D of gamma is 0 is a closed form. That immediately tells me that all exact forms are closed because of D square being 0. So, any exact form is closed. So, this implies all exact forms are closed forms. But is the inverse true? That's what Poincaré's inverse lemma. Is the inverse true? Are all closed forms be expressible as D of something? So that raised a lot of proofs and long time back. I'm talking Poincaré's early 20th century, all these things were done. I will not spend on it because I myself have not gone through the proof. The standard literature says that in a local neighborhood, in a given chart, any closed form can be written as D of another. But it's not globally true. You can't do it all over the manifold. Locally, any closed form can be expressed as an exact form. Okay. But I have not done the proof, so therefore I will not spend time on it.
Is it related to Poincaré?
Yes, Poincaré's conjecture initially, but then it was proved later that locally, in a small neighborhood, in a chart, you can always express a closed form as as D of an exact form.
That's why
Yeah.
that went to Perelman and all those people from
Could be. I don't know the history. Yeah, could be. Yeah, so, all these are important when you express things in terms of integral of forms. It's a beautiful thing, but we will not have time to discuss on it. So, Gauss's theorem, Stokes' theorem, they all become special cases of just these results. Okay? Okay. So, before I leave differential geometry, I'll tell you what metric is in differential geometry. So, we have so far, after introducing metric, I will introduce Hodge-star duality, but because it uses the metric. Yeah. This is a beautiful area, and I urge those who find it beautiful and who find all these analysis very fascinating, they can pursue differential geometry at length in detail. Right, now for the first time I am talking about metric tensor. So far all our analysis never bothered about is there a notion of metric, can we find out magnitude of a vector and so on. Never talked about it so far. Metric G it's a bold G, it's not, because the determinant of a metric is also written as G. Metric G is obtained by a tensor product of one form. So metric G can be, now I am going to mu nu index because that's what we will be using, is G mu nu. We are now talking about fields. They are all defined all over the manifold. Is dx mu one form, tensor product dx nu. And therefore, because tensor product and mu nu being summed over itself tells me only the symmetric part of G mu nu is important. If there was any antisymmetric, this would have become 0 because this is symmetric. Tensor product is symmetric. Okay. So in other words, what is a metric tensor from differential geometric point of view? It takes two vectors and produces a real number. So if G, this object, acts on two vectors u comma v, remember u and v are abstract objects, then this will be G mu nu of x. How does dx mu act on u? It will be x. How does this? Then you have that result, d of x mu acting on v. And how does this act on v? It is dx nu acting on, I've written first u, then v. But u itself, because I am choosing basis vectors, so I can write it as G mu nu of x d of x mu comma components. In terms of components, I can always write it as u nu del by del x nu. Okay. All right. And this is, okay, so this, since nu has been used, I will call it alpha. And here d of x nu comma v of beta del by del x beta. Okay. And this is a linear thing. This operation is linear. U alpha will come out and this will act on it. So this we know. So let's explicitly write, because we are doing it for the first time. No harm in explicitly doing it. So this operation of a one form on vector field is a linear operation. That means U alpha will come out, and this is simply dx mu del by del x alpha. And v beta will come out. This is a linear operation, v of beta d of x nu del by del x beta. So I will go straight to the top. This is same as G mu nu. I'll suppress the arguments. These are all fields. U alpha. These are all fields. They are all dependent on fields. Dx mu del x mu is simply del x mu by del x alpha. Del x mu by del x alpha multiplied by v of beta dx nu del x nu by del x beta. This is simply Kronecker delta, G mu nu U alpha V beta and when they are summed over, so only when alpha is new it will contribute, here only when beta is new it will contribute, and we get G mu U mu V nu. Okay. So in other words, when G acts on U comma V, then you get the usual result G mu nu. In the tensor component, tensor calculus notation, you get back. This is how we calculate the magnitude of U mu and another V mu vector using the metric. So this is a differential geometric part, and this is what we get back, the usual standard tensor calculus result. Okay.
Sir,
Yeah.
till now, whatever we have done, we have not discussed about the distance
Metric.
notion, nothing.
Distance, no, absolutely, absolutely.
As and when we are introducing the metric tensor, there comes the inner product and
Yeah.
implicitly comes the distance notion.
It is strictly not an inner product in the vector space sense, because remember the inner product result, that if I take a vector and take the inner product with itself, then one of the properties of the inner product is that inner product of U with U, if it is 0, then U must be 0. But we know that for a Lorentzian metric this is not true. So therefore, the inner product that we have, the notion of inner product in vector space is not same. But it's an important point, because I will talk about, some of my thoughts related to this I'll talk about soon. Yeah. Okay. So we understand therefore the metric as a object constructed as a tensor product of two one forms, and then how when it acts on vectors what it gives. Okay. Now I will define the Hodge star operation, because that's one of the problems that Bhashwati Hodge star operation. Hodge star operation uses the metric, and that's the reason I first had to introduce the metric tensor then. So Hodge star operation is an operation that takes omega k space, the space of k forms, to the space of k plus 1 form, to n minus k forms, where n is the dimension of the manifold. Here, before I should have defined that thing. The so-called Levi-Civita symbol I should have defined. Okay, in higher dimension. We all know about epsilon, mu, nu, alpha, beta in 4 dimension, but the generalized notion, let me first introduce that. The Levi-Civita notation, epsilon, J1, J2, Jp, I1, I2, Ip is such an object. It's totally antisymmetric. Means what? It is plus 1 if these J's, Ji's, if Ji's are an even permutation of I's. If J's are even permutation of I's, because that means J1, J2, Jp are even permutation of I's, minus 1 if odd permutation, 0 otherwise, Okay. So because it's 0 otherwise, that means it's completely antisymmetric. Any 2 index you flip, you'll get a negative sign. Okay. And the Hodge star operation, with all indices, I must not make a mistake, because details are important in the definition of the Hodge star operation. Yeah. So remember, we have a metric and we will define this G to be the determinant of the metric. So what do I mean by that? G mu nu, mu is going from I1 to, mu is going from 1 to n, nu is going from 1 to n, but I can therefore treat it as a matrix. Okay, I can write it as G11, G12. So if I write G mu nu as a matrix, because any two component object can be written as a matrix, and therefore it's a square matrix, and I can take the determinant. So small g is the symbol for determinant of the metric G mu nu. Then the star operation does the following. If alpha is a P form, then star of alpha, which is nothing but star of any P form, after all, is 1 over P factorial alpha I1, I2, IP. Okay. So star of this object, let it be here. I'll write it here. By the way, although I am using the coordinate basis vectors for the one form, but you can do it with arbitrary basis vectors. Star of that object, so I'll come here, is equal to square root of the determinant of the metric tensor. By the way, the determinant, I have assumed that the determinant is positive, but yeah, it's better to, because when we have Lorentzian thing, that will be negative. So therefore, I'll write it as mod, square root of mod of G divided by n minus P factorial, n factorial That's why the metric is important, because the metric has been used to lower and raise indices of the generalized Levi-Civita tensor. That's why you can't define the Hodge-star duality operation without the metric. So when I write down, you will understand what I'm saying. Multiplied by no. Yeah. Okay. So this is the definition of the Hodge star operation on a P form, and you can see this. By the way, this lowering of indices and raising of indices has been done using the metric tensor. We will do that because once we start talking about our four-dimensional space-time and general relativity, we will be doing that operation very often using the metric tensor. That's the reason why metric is required as to how to go from the standard definition to this, right? And it is obvious that this is n minus p form. So Hodge star operation is taking a p form to n minus p form. Okay. All right. From here, you can easily see that Hodge star operation of a 0 form is simply the n form. Okay. So in other words, the Hodge star duality maps n form to 0 form, and in general, of course, p form to n minus p form. And in your tutorial problem, we have seen how to write down the inhomogeneous Maxwell's equation in terms of the Hodge star dual. And there, of course, we were, the problem was on Minkowski metric. So Minkowski metric, if you write the metric eta mu as 1 minus 1 minus 1 minus 1, probably Bhashuddhi would have written it as minus 1 1 1 1. Doesn't matter, the determinant is negative. And that square root of this would have been 1. So your metric might not have appeared explicitly because this factor would have been 1 for the electrodynamics. And you would have shown that the inhomogeneous Maxwell's equation is nothing but d star f is star j with some factors. Okay. Is there something else I should have? Okay. The only last thing I will say while I'm staying in differential geometry is that tutorial problem, you were told that your vector potential was a one form, which is a mu dx mu, and then the two form f was written as t of a. Okay. The standard way of writing it in 4 vector notation, f mu nu is del mu x a nu minus del nu. And you get back your standard Maxwell equation. But supposing you have a magnetic monopole, was magnetic monopole discussed in the tutorial? If you have magnetic charges, just like if you have electric charges, the divergence of electric field is 4 pi electric charge density. But if you have magnetic charges, then divergence of magnetic field will not be 0. Divergence of magnetic field will be 4 pi into magnetic charges. Can you still use differential geometry? The answer is yes, you can do it, but you cannot write f as dA. Because if you write f as dA, then df by definition, because then f becomes what? An exact form, and d of an exact form is 0, so d of f is 0. This result is true only if magnetic charges are not there. Okay. So if you have magnetic monopoles, you cannot write f as d of a. There are other ways of writing f, and then the magnetic charges d of f will be the magnetic charge density. Okay. That's the only remark I wanted to make. Now, how much time we have? Can I take a little 5 minutes? Yeah, okay. Now I'm going to leave the differential geometric approach, because I have already made the correspondence between differential geometric arbitrary tensor with the tensor components. Now I'm going to use, now I'll come specifically to physics 3 plus 1 dimensional space-time manifold. So far we were doing arbitrary general thing. Okay, arbitrary general thing is very important. That's why string theory, they use all advanced notion of differential geometry, because for them the space-time is 10-dimensional. Okay, but now we come down to the standard general relativity, where our perceived world is 3 plus 1 dimensional. I'll just take 5 minutes so that I will tomorrow onwards I'll talk about curved space. Today I'm just some basic things about special relativity. Many of you know. I'll just reiterate why it is important. So we know that the Minkowski's formulation of general of special relativity is simply this, that when you go from one inertial frame to another inertial frame, the inertial coordinate system, we have already talked about what are inertial frames in my first lecture. So when you go from one inertial frame to another inertial frame, or you can think of you are an observer in one inertial frame, there's another observer in another inertial frame, how are the coordinates related to each other? So that's another way of writing it. Then you know that they are related by the Lorentz transformation, where lambda mu nu are the components of the all those v by square root of 1 minus v square by c square, the Lorentz gamma factors come in. So there is a standard, the most general Lorentz transformation, which includes the boost, meaning moving, and also rotation of the Cartesian coordinate system. Then under this Lorentz transformation, what is the thing that Minkowski said, which Einstein was not using it, is the Minkowski metric tensor eta alpha beta is an object that is invariant under Lorentz transformation. So x mu go to this, eta alpha beta is a second rank tensor, it should go as this is a second rank tensor, it will transform like this. But what Lorentz realized, Minkowski realized, this object is same as eta alpha beta. So the definition of a Lorentz transformation is those 4 by 4 matrices, lambda alpha beta is a 4 by 4 matrix. Those 4 by 4 matrices for which when you apply it on eta mu nu, it get back eta alpha beta, they don't change. And what is eta alpha beta? In my notation, eta alpha beta, if you write it as a matrix, it is, in my, you can use any notation, minus 1, minus 1, minus 1. In other words, what this is corresponds to is ds square, the invariant proper distance is c square dt square minus dr dot dr. If you probably Bhashpati use minus 1 plus 1 plus 1, then this will be dr dot dr minus c square dt square, and eta alpha beta will be minus 1 plus 1. So one can go from one. So this is standard. Okay. So in Minkowski's way of doing it is completely geometrical, and unlike Einstein's thing, Einstein was a physicist. He felt everything in terms of forces, being muscular and all that. He was a thorough physics way of thinking. In his, there were all these eta alpha beta never appeared. Yeah, so what I'm trying to say is that Minkowski tensor is a special tensor which is invariant under Lorentz transformation. Invariance is this, that if you do the Lorentz transformation of eta mu nu, you'd get back the same. Okay. By the way, there is another tensor which is completely invariant under proper Lorentz transformation. It's actually epsilon mu nu alpha beta, and that I got interested into differential geometry because of that fact. When I realized it, I said that if in general relativity eta alpha beta becomes a dynamical field g mu nu, why shouldn't the Lebesgue tensor epsilon mu nu alpha beta, which is also invariant become a dynamical field. So I introduce, and epsilon mu nu alpha beta is a 4 form. So I introduce a 4 form, dynamical 4 form. I wrote some papers and using that Chern-Simons. So I don't know, I've been claiming that this 4 form field can act as both dark energy as well as dark matter. This is my theory. Let's see what happens in future, whether dark matter turns out to be particles associated with 4 forms. After all, only nature selects which is the correct theory. Anyway, let's move on. Okay. So, we know, therefore, my interest into differential geometry came from that realization. Earlier, I had not learned much of differential geometry. So, I had to learn on my own to sort of further my idea. Right. So, in other words, if you have an observer, you have done the world line, particle production. So, if you are an observer moving along a world line, although I have drawn a world line, strictly I should have been drawing upwards because time is normally put in the vertical axis, but it doesn't matter. We understand what we mean. So, if it is going from one point to another point in the event, so here are the 4 coordinates of this event and here are the, then the proper time which the clock of the observer measures. Now, this is very important. It doesn't matter whether you're moving at uniform velocity or accelerated, doesn't matter. The observer need not be an inertial frame, but maybe making an accelerated. But the clock, if he's carrying a good clock, I talked about good clock in my first lecture. If he's carrying a good clock, the proper time elapsed from here to here will be nothing but square root of ds square by c square. And what is ds square by c square? It is 1 over c square root of eta mu nu dx nu dx nu. If it is moving, if it is an inertial observer, what I have said, you will agree with me, all right? Well, it is uniformly moving, that's the time it will, because if the inertial observer, if you are an inertial observer and in your own frame, dx, dy, dz will be 0 and it will be c dt, obvious. But how is it that even if it is accelerating, I am claiming that this will be the proper time? No textbook will tell you this. And by the way, this is what is the standard thing. When you are moving, even whether you are accelerating on that, the proper time, if you are carrying a good clock, proper time elapsed, and total proper time you have to integrate it, of course. You integrate. Why is it true? It is because even if you are accelerating, if you are carrying a good clock, at every point there can be a co-moving inertial frame. You are accelerating, but at that point you can compare your time with a co-moving inertial frame, and that will agree with that infinitesimal part. Of course, after some time you have gone somewhere else, your velocity is different, but there also you will have another co-moving inertial frame who is at rest locally with respect to you. There the proper time will agree with you. And therefore, if you are carrying a good clock, whether you are accelerating or not, this will be the proper time elapsed in our frame. This is the proof.
So this basically comes from the invariance of this length element.
Not yet. I have not yet talked about general relativity. So in accelerating frame, we are not yet talking about transformation. Invariance, I know invariance in inertial frames, but if I am accelerating, I don't know that it doesn't fall under the purview of special relativity. So I can't talk about that, but at the same time, physically I know, if I am carrying good clock and I am accelerating, how do I know I am carrying a good clock? It must agree, the time must agree with a co-moving inertial observer. and if it agrees with co-moving inertial observer, then this integral must be the real time elapsed. Okay?
That is the invariance of the infinitesimal
Invariance under which transformation?
Lorentz transform.
But I am an accelerated observer. You can't use Lorentz transformation.
If you take an infinitesimal of
Within that infinitesimal transformation, for a short time I am at rest with respect to a Lorentz observer, but I am at rest with respect to Lorentz observer. There is no transformation. So I shouldn't be using any transformation. But if I am carrying a good clock, the good clock must agree with a co-moving inertial observer. Then the integral of this, whether I have accelerated or not, must agree, must be the proper time elapsed in my frame.
So in this case, the proper time and the coordinate time are same.
Wait a minute. The proper time of a co-moving inertial frame will be the coordinate time, because the co-moving in his frame, his coordinates, his spatial coordinates are not moving. His coordinate time is 3. But here is something else. Here I am not an inertial frame. So I don't know what do I mean by coordinate time. But what I know is this entire point. This way of realizing what the proper time is, solve the twin paradox. You can prove that if this goes around and comes back, the total time will be less than a person who has stayed back. It will solve it. Why is it obvious? You don't have to even do calculation, because supposing my twin remains where he was, I go back and come back. And I claim that this is the proper time elapsed. Then this will be less than the time elapsed, because this has c squared dt so minus dr dot dr. It will always be less. We are subtracting my motion. So this solves the twin paradox. See, there is nothing funny about twin paradox.
I have a confusion in the sign convention, because is it a delta square is equal to minus eta alpha?
No, the way I have written the metric.
Okay, plus minus.
No, the way I have written down my metric c squared dt squared, d tau is 1 over c ds. But if you had written the as dr dot dr minus c squared dt squared, then you would have put a negative sign. It will be square root of minus ds squared by c squared. Okay, so I think I will stop here. I will not. This is the only thing I wanted to talk about special relativity. But as I said, for any measurement in GR, how do you measure things? You have to always fall back on a local inertial frame. That we will continue to do. But tomorrow I will show one important thing that Anuj will be using for the tests of general relativity, that how is G00 related to the Newtonian potential. From this analysis only I will show. That's why I first did the relativity. Well, a little thing I will show. A little thing, because tomorrow I will extend it. Yeah.
To resolve that twin paradox thing, you need to use the fact that the ds square measured by the two people are the same.
Exactly.
You need to use that, right?
Yeah, but that is only true for the inertial observer. Why is it true also for an accelerating observer? That is the argument I gave. Yeah, so the only one small thing I will do today, because tomorrow I am going to extend it so that Anuj can cover the tests of general relativity, is this, that you can show that the action for a free particle is rest mass into c into ds. The ds is square root of ds square. So it is invariant under Lorentz transformation, and therefore it's an m is the rest mass, it doesn't change. So therefore this, let's write down in detail, is square root of 1 minus, okay, let's write down carefully, c square dt square minus dr dot dr. This is the last thing I will do, and then we can discuss. That is action. But someone will come and say, hey, but when we did Newtonian mechanics, our action for a non-relativistic particle was nothing like this. It is the kinetic Lagrangian was the kinetic energy. But I will now prove it follows from this. Okay. First, let me rewrite. So this is same as minus mc. What I'll do is c square dt square I'll bring out so that it's c dt 1 minus 1 over c square dr by dt dot dr by dt. It's the same as, so if a particle is moving about, then the same as minus mc square integral 1 minus v square, v vector square, v dot v by c square d. Okay. The dr by dt is the velocity vector. But then you will say that, but I know that for a free particle in Newtonian mechanics, the Lagrangian is simply half mv square, so that the action is integral of half mv square over time. Is it still true? Yes, it is true, because for Newtonian approximation, is what? The velocity v is much less compared to c. And v dot by v c square is a negligible quantity. So I need to take, when I take square root, I need to take only the first term. And then my action therefore is minus mc square integral 1 minus half v square by c square dt, which is nothing but this from t1 to t2, let's say. This is minus mc square. This is just t2 minus t1 plus c square gets cancelled. You get half mv square dt from t1 to t2. This is your standard action for a Newtonian particle, free particle. What about this? Someone will say, what about this? This is arbitrary constant. Arbitrary constant, when you add to the action, the equations of motions will be affected by it. So I have made so what did I do? I have made a correspondence between the special relativistic action for a free particle and how, when the velocities are much less than c, how it reduces to the action you are familiar from your classical mechanics course for a free particle in the Newtonian case. Tomorrow I will say, oh, that is fine, but we are not in a flat space-time, there are metric. If you introduce metric, what happens? And there I'll make a correspondence with the G00 component of the metric tensor with the Newtonian potential. That's why I have to show this, so that tomorrow I'll show what is the Newtonian approximation for the G0. Okay, I think we can stop here.